Okay. Well, this talk actually has a very close relationship to the infometrics workshops, and I thought I'd just make a little prologue to explain some of those relationships. Some time ago, I started a conversation with a friend of mine, Dave Oliver, a physicist that I met at MIT back in the early 70s, on the problems of understanding information theory and probability in relation to quantum mechanics. And he, at that time, pointed me to a paper on effective complexity by Murray Gell-Mann and Seth Lloyd. And that led to an interesting set of conversations that I had with Lloyd and Gell-Mann out in Santa Fe about this paper. This paper is interesting to me primarily because it's about model choice or theory choice. That is, how do you decide, if not what is true, what we ought to proceed on the basis of thinking is kind of the closest we can come to the truth given the information that we have. It's not phrased in Bayesian terms, Gell-Mann and Lloyd, but it does recommend a principle for theory choice, which is that you should choose the theory that minimizes the total, what they call total information, which is for them the sum of the Kolmogorov algorithmic information content of a theory and its entropy. And at the same time, they argue that you should that this will lead to maximizing entropy. And I was very puzzled as to how minimizing the sum of something that had entropy in it would maximize entropy was one of the questions that motivated this discussion. And it's led to a rather interesting outcome. A second line that has to do, well, from that line came interactions here at the Infometrics workshop with Peter Adrians, in which the close relationship between the two-part code and a Bayesian formulation of theory choice began to be apparent, and that led to some further interactions between Peter and David Oliver and myself, which developed some of these ideas. So that's a key strand. Third, at the Infometrics workshop, I met Teddy Seidenfeld, and after the workshop, Teddy wrote me an email, rather what I call laser question email, which said, you know, just how much of a Bayesian are you? And do you really believe in maximum entropy, or do you really believe in Bayesianism, because they're not the same thing? And I was somewhat taken aback by that because I learned all this stuff from reading Ed Janes, and he's very keen on both maximum entropy and Bayesianism. And that led me to read some papers of Teddy's that make some interesting points, which is that it's not very easy to state a prior which leads to maximum entropy outcomes. Now, Ariel has addressed this indirectly already. In fact, my talk is very closely connected to both Peter and Ariel's talk. And I read Teddy's papers with my graduate students at the New School, Alice Scharfenacher and Gregor Semyenyuk, and that led to some more thinking about this problem, which is another strand of this paper. And the last one has to do with Marcus Schneider, who is sitting here today, who was working in his PhD thesis work on analyzing wage data from the United States. And it turned out that a critical question for Marcus's work was how you bin the data. And that made me begin to realize something that Jorma Rissanen had told me, which was that there are no unparametric models. There is no such a thing as a non-parametric model because, for example, binning is a form of parametrization. And that led back to the question that at Santa Fe is called coarse graining. That is exactly how do you choose the categories into which you organize data, and this this paper addresses that problem. And it's too small. Is there any way to make it bigger, do you think? I just don't know how to, because I don't think people will be able to read it. No, probably there isn't. No. Oh, that's good. That's better. Okay. I'll skip the abstract because, except now I have to scroll. Okay. So let me just sketch the setup, which comes from Gelman and Lloyd, and what happens when you put this into a certain Bayesian framework, and talk a little bit about the relationship of it to Peter Adrian's work, and perhaps I think there are also some connections to what Ariel told us. So the data in, as Peter calls it, for the Gelman-Lloyd setup is a string. It's a finite string. And we might as well think of it as a finite binary string because there's no loss of generality. So it's just a big string of ones and zeros. And that string might represent, for example, the state of the molecules in a perfect gas. This is an example I'll use sometimes. Or maybe that string is actually the encoding of the complete works of Shakespeare. Or maybe that string is just the result of a very long series of quantum measurements on a spin experiment of some kind. Anyway, that's the basic object. Gelman has the idea that you want to explain things through the concept of an ensemble. So for Gelman, the whole idea is not that you take a string and try to explain it, but you try to assign a probability to it. So an ensemble, in the broadest sense, is just an assignment of probabilities to, or frequencies to strings. The Kolmogorov algorithmic information content, the AIC of an ensemble, is the length of the shortest program which, when supplied as an input to a prefix-free universal Turing machine, along with the string itself and a precision n, halts with n bits of this probability assignment on the tape. So we're shifting gears here from thinking about the complexity of the string to thinking about the complexity of the ensemble, of an ensemble that somehow best represents a particular string. And Gelman and Lloyd and I want to think of this as an abstract model of theory, choice, and science. So it's very abstract, but it has many of the elements that you run into in almost any scientific enterprise. Okay. So the way I'm going to approach this is through the Bayesian framework, which we've already seen. Amos mentioned it. See, I can't see the screen, so I have to look. So the Bayes theorem in this sense is just this decomposition of the definition of conditional probability that says if we call H a hypothesis or a model or a theory and D data, that the probability that we assign in Ariel's sense, that is the degree of belief in it, given what we know, the data, which we can think of as the information, has to be equal under the rules of probability to the conditional probability of the data given the hypothesis. So in the case of the ensemble, that's going to be the probability that the ensemble, if we think of the ensemble as the hypothesis, that's going to be the probability the ensemble assigns to the data, times the prior probability we assign to hypotheses, which is going to play an important role in what I have to say. And then this P of D at the bottom is just a normalizing factor to make sure that you have a well-determined probability distribution. So what this says is that you are going to, if you have a class of hypotheses such as ensembles, and you have a prior over those ensembles, this posterior gives you a definite posterior probability for any particular ensemble. There's any particular way of assigning frequencies to the strings. And it's important to realize that there are really two levels of probability here, and it's a very confusing thing, and I wish I could find a better terminology for it. The ensemble assigns a probability to strings. The P is assigning probabilities to ensembles. This is also inherent in Ariel's updating idea, because what you're updating are probability distributions. So I tend to like to use the term frequency for the ensemble assignments and the term probability for the posterior probability and the prior probability of ensembles. So if you think about things this way, you can see that the, that the posterior probability, is there a, maybe I can make this work? No. No. Okay. The posterior probability of an ensemble given a particular data string X is equal to the probability of X given the ensemble, which is just the frequency the ensemble assigns to X, times a prior probability of the ensemble. Or we could take the logarithms, as Peter points out, in this very elegant way, and you see that the logarithm of the posterior probability of the ensemble can be decomposed into the logarithm of its prior probability plus the logarithm of the likelihood. And this is the two-part code that he referred to, Riesenen's idea. Now, the other key point in this way of thinking about stuff is that is the Shannon theorem. So what Shannon's theorem, the way I look at Shannon's theorem, is a very powerful theorem because it says, as Peter outlined, that you can always find a code that assigns minus log of the probability of an object to that object or that message. But it also has a converse, which is that if you have a code, you're implicitly assigning probabilities. So there's a kind of a duality between, a very fundamental duality between information in the sense of coding information and probability assignments that's established by Shannon's theorem. So another way of looking at this posterior probability, log posterior probability, is that the two-part code, it minimizes, if you're going to maximize the log posterior probability, you're effectively minimizing the two-part code length exactly in the terms that Peter has already described. Okay. Now, at this point, we diverge a little bit from what Peter said, because we're now going to enter the world of Murray-Gell-Mann, and I think this may explain some of the disagreement that you and I had last night, and also some interesting things about the pictures that you showed us. So Gell-Mann says, he says, you know, it's a very funny thing in science that you take really hard problems, like the behavior of a perfect gas, and how do we solve them? We make them into an even harder problem. Because instead of just thinking about the state of the gas, we try to think of the state of all the possible states of the molecules in the perfect gas. So it seems like we're complicating the problem, but it turns out that complicating the problem in this particular way is the key to solving it through the methods of thermodynamics and statistical mechanics. So for Gilman really wants a abstract representation of this kind that includes statistical mechanics as a kind of a central possibility. And the point about statistical mechanics is that it is based on what I call energy-like constraints. So for any ensemble, if we have a function f of that's defined over the data strings, which might be their energy if they are a description of the state of a gaseous system or whatever it might be, it really doesn't matter. But that's just the expectation given the ensemble. And that is a constraint. So now what we're doing is we're going to maximize the log of the posterior probability subject to one or more of these energy type constraints. And that, at the first glance, I didn't think that was very important. But in fact, I think it is very important as far as the details of the probability subject to one or more of these energy type constraints. And that, at the first glance, I didn't think that was very important. But in fact, I think it is very important as far as the details of the reasoning go. And this also touches on Teddy Steidenfeld's point, because in response to Teddy's critical paper saying what is the prior that gives you maximum entropy, Jaynes wrote a very interesting paper, although in some ways one of his less, in my view, less convincing papers, in which he said, well, you know, there's really a duality here. There's two kinds of information. One kind of information is what he calls exact measurement. And what he means by an exact measurement is something like what a physicist does when you measure the temperature or the energy of a system. So it's a point, it's exactly this kind of constraint. That's what he means by an exact measurement. He says when your knowledge of the system comes in the form of exact measurements, then you use maximum entropy. But he says if your knowledge of the system comes from actually sampling part of the system, you know, pulling out a certain number of molecules by whatever method you can use, then that doesn't give you an exact measurement because no sample can tell you anything about the whole ensemble probability assignment. So it's in that case that he shifts gears and says he's going to be a Bayesian, that you have to have a prior probability. I confess, as an economist, I found myself extremely, and my students found ourselves extremely puzzled by this notion of an exact measurement, which is second, you know, like breathing for the physicists. But when we started to try to think about what an exact measurement was and how you would do it in economics, we didn't know. Okay, so let me discuss, actually the whole point of the talk is just to discuss these elements. So what do we take as a prior? Well, you go back to this very seminal paper by Ray Solomonov, which is echoed in Kolmogorov and in Chaitin and various successor papers. And Kolmogorov says, well, if you want a universal prior, here's the way you do it. And we're now thinking about priors over ensembles, not over the strings, but over ensembles over the strings. Then the prior should be inversely proportional to the Kolmogorov, Kolmogorov information content of the ensemble. So we don't like ensembles that take a lot of bits of computer program to compute. We like ones that take a very small amount of computer program to compute. This is sometimes called the universal prior, and then we can plug that in, and we see that now the problem becomes to maximize minus k of the ensemble minus the logarithm of the probability that the ensemble assigns to the data string x. And let's look at each of those. elements. And here is where, if there's any contribution of mine to the thinking about this, I think this is where it lies, and maybe Peter was suggesting that he didn't completely follow why I did this, but I was trying to think, well, all right, what kind of computer program would you write to compute an ensemble probability, to compute ensemble probabilities? And it occurred to me that you really would probably, now I can't prove that this is the only way to do it, but a way to do it would be to divide the program into two pieces. So the first piece is basically a program that sorts the strings into different categories. So it divides the strings up into some number of subsets. Some of those subsets might just have one string in them, but I'll explain that that's really rather unlikely in any practical circumstance. And this is what at Santa Fe they call coarse graining. So you say to yourself, okay, I'm going to regard all of the strings that the computer program can't tell apart because it puts them in the same subset. I'm going to regard all those as effectively kind of equivalent from the point of view of the ensemble. So the ensemble can only assign different probabilities to different subsets of this type. So if you have a computer program that computes an ensemble and therefore does coarse graining in this sense, and this is where the intersection lies with Marcus Schneider's problem with the wage income data, because the question is, well, what are the optimal bins? Actually, the way that the government statisticians do it is they kind of just make up bins out of their head. There's no attempt made to really study what an optimal binning is in any sense. But this, I'm just going to, you're just one step ahead of me. Okay, so the second part of the computer program is going to assign frequencies to these bins, to these subsets. And then what the ensemble has to do is it has to divide up that probability equally among all the strings in that subset. Now you can see that for many big, long, complicated strings, like the works of Shakespeare, it's going to take a very long computer program to recognize the complete works of Shakespeare exactly, right down to every detail, right? You can write maybe shorter computer programs that'll do things like say, does it look like this is a work in the English language? This actually intersects with Peter's little example about the letter frequencies, word frequencies. Does it look like it's a work, does it look like it's a piece of text from the late 16th and early 17th century in English? And so forth. And so you might narrow it down more and more. And if you stop and think about it, actually even the concept of the works of Shakespeare is a little bit funny because we know there are many different editions, many different sources, many variants, what they call variants. So actually the works of Shakespeare is very naturally a kind of a subset of strings. It's not one particular string at the best that you could possibly think of it. This also has to do with Platonism and where these ideal types come from. Well, the point is that these two aspects of assigning ensemble probabilities can be separated. That is, you could have a certain coarse graining, and then you could assign a lot of different probabilities to it. You could assign probabilities to maximize entropy, or to minimize Shannon entropy, or to maximize Salas entropy, or any one of a large number of rules. Murray Gell-Mann is going to come and look over your shoulder and say, you have to assign these probabilities in such a way that they meet the energy constraint. So for whatever coarse graining you have your computer program set up to produce, it better be that you choose among the probabilities that satisfy the energy constraint. And I think this is where there's a divergence, because I think that problem with an energy constraint is going to be a lot smoother, for example, than the unconstrained problem that you are working on. Okay, so we now have basically solved the problem, and I've reached the end of the talk because, except I'll just put a little picture up. So what is the story? Well, the two-part code is basically going to be equation 10 here. The Kolmogorov complexity of the ensemble is going to be the Kolmogorov complexity of the coarse graining, that is the program that does this sorting problem, plus the logarithm of the number of bins minus the entropy of the frequency distribution. Now, why does the frequency distribution come into it? And why do you maximize? This comes back to my basic question with Gelman and Lloyd. Why maximize entropy rather than minimize entropy? So you definitely want, in order to minimize the Kolmogorov algorithmic information content, the program has two pieces. One is the part of it that does the coarse graining, and the other is a table, basically, or an indication of what the frequency, a coding of what the frequencies are. So I believe that what maximum entropy is doing, and this is something that I'd like your advice on, that what maximum entropy amounts to is to say we're going to code frequency distributions according to the Shannon code, which is inversely proportional to the entropy of distributions. So we're going to take low entropy distributions, and we're going to give them the high entropy distributions, we're going to give them the shortest code words, and then we're going to work our way down. And therefore, in order to do this grand maximization problem, we are going to wind up choosing a frequency distribution that satisfies the energy constraint and has the highest entropy. What I don't know, and what I would be very interested in your opinions and feedback on, is why maximize entropy as opposed to minimize entropy? Because you could code them the other way around, right? You could start with the very lowest entropy distributions and give them the shortest code words, and then work your way up to higher code words for higher entropy distributions. And also echoing Ariel's point, why Shannon entropy? Because any measure, entropy-like measure, could be used as the basis of coding. Okay, how am I doing on time? Still have 7 minutes. 7, okay, that should be plenty of time, except I can't get the... Okay, so we can think of the final grand problem that emerges from this way of thinking of this problem as maximizing, let's look at this bottom line 13. So we're going to choose the ensemble we're going to choose the ensemble to minimize the Kolmogorov complexity of the coarse graining minus the number of categories in the coarse graining plus the entropy of the coarse graining. And then what's left is to pick out the data string. But picking out the data string now just means that it has to share probability with all the other data strings that are in its coarse grain partition. So what you would like, other things being equal, is to get that as small as possible. You want the data string to be in as small a partition as you can. But you can see that a consequence of this is going to be that other things being equal, if you code the frequencies, I'm sorry, I knew this was, if you code the frequencies according to their entropies, then you're going to wind up assigning a maximum entropy distribution subject to the constraints given the coarse graining. Now, whether this actually goes any distance to satisfying Teddy's question, I would be interested to know, but it seems it's the best that I can think of. So if you want to have a picture, and this is part of this convergence of economics and physics that Ariel referred to, because this is a classic economics picture, we're measuring a kind of a generalized entropy along the horizontal axis of ensembles. So this is supposed to be a picture of the space of ensembles. And we're measuring the algorithmic information content of the coarse grain partition in the vertical direction. So very much like Gelman and Lloyd, what you're doing when you're maximizing this posterior probability is you're maximizing the sum of those two things. Now that's not exactly what they called total information, but it's rather similar, and it seems to me it makes makes a little more sense. So that creates what economists would call indifference curves, which are these straight dashed lines of equal posterior log posterior probability. The constraints establish this gray area here. So that's all the ensembles that meet the constraints, which I've stylized as a nice sort of production function from economics. And where you go to maximize posterior probability is to the place where the indifference curves are tangent to the trade-off that's established by the actual data that you are working with. You can understand this diagram a little better, which is that I kind of like this picture of what a scientific theory is. It may not, it's maybe too constrained to do the aesthetic things that Peter wants to do with all the things, because he wants to deconstrain it and deconstrain. But if you're dealing with typical, what we think of as more scientific problems, it seems to me pretty reasonable. So what it's saying is, okay, here's how you approach this. You try to figure out a theory, that is a computer program, that recognizes some structure in the data that you have. And the way you recognize that structure is by sorting the data into bins, that is some kind of coarse graining. And the trade-off is that you can always get finer bins, but you're going to write a longer computer program to do that, right? So if you get finer bins, you're going to shrink down the bin that has the data string in it, and that's going to improve that part of the two-part code, but you're going to let the other part of it get too big. And the main wrinkle here is that a part of the computer program, a sort of separate part, is the assignment of probabilities to the bins. And that assignment of probability to the bins is actually dominated by the constraint issue, by this exact measurement issue, because that's why you're bothering to do that at all. And therefore, but the motive that you have in choosing a frequency distribution to assign is actually how compactly you can code that frequency distribution. And it's in that part of the algorithm that maximum entropy appears, maybe where you didn't expect it to appear. Thank you. Amos, did I get to your question?
Yeah. Two things. Why Shannon is easy to answer. I mean, not even from axiomatic approach, because any other higher order entropy like Sally-Sorenya would put different weights on the different parts of the distribution. So it's as though you put priors. So, I mean, just for practical purposes. So not even axiomatic approach. But the point that I have is about binning, which bothers me, because if you search for the bins from the data, you don't know a priori whether your theory is continuous or discrete. And then by forcing a discrete system to go to the continuum when you look at very, very fine bins, or vice versa, you're actually modeling based on supposedly observed information the wrong system. Because if the system should be modeled as though it is continuous, you cannot bin it, and vice versa. And even, you can try it, even if you hold the mean value, the constraint that you put constant, things will change. You will have a phase transition or transition when you move from the continuum to the discrete or vice versa.
Okay. Well, let me try to answer both parts because I think they're both very interesting and relevant points. Let me take the second one about the continuum issues. We're dealing with computable functions here. So that means that we're always actually dealing with countable or, practically speaking, finite partitions. You just can't get around that, I don't think. And you're dealing with finite assignment. You're dealing with computable frequencies. The second point about Shannon. Shannon plays a role in two parts of this argument. The first, and in my view more important part, is that the Shannon theorem establishes a relation between these Bayesian probabilities, the probabilities over ensembles that allow you to choose among ensembles as theories. It plays a key role in connecting that up through Shannon and through the two-part code to the compression issue. And that, to my mind, is the more important part. It plays a secondary role in coding the frequencies of the ensemble. And there, that seems to be much more contingent. I mean, that could be, you might minimize it, you might use a code based on minimum entropy or a code based on Solace entropy or Renyi entropy. Yeah, I myself am quite uncomfortable with this idea of typicality because I find it hard to translate it in a simple way into Bayesian, into a Bayesian prior. I think, see, what's happening here, now let's think about what's happening here. If you have the constraint, if you have an energy constraint, okay, so you're trying within the energy constraint to make the bin that has the data set in it as small as possible. Well, that's something like typicality, right? Because the data set, the data string just shares all the probability with whatever else is in that bin. So the smaller you make that bin, the more typical you make the data set. Yeah, but I think that's already subsumed in the maximum posterior probability formulation, because how are you going to reduce the random? You're not allowed to code the bin, because the bin has already, the computer program has already done the best it possibly can in sorting the strings. So So I think that's an interesting point, but I have the feeling it might be.